All right, so now we move into lesson 2, which again, just like lesson 0 and 1, is going to build out some more fundamentals. But this is a really critical lesson for not only kinematics, but setting up the definitions that will be used all the way to the end of Physics 20. So we're going to look at scalars, vectors, distance, displacement, speed, and velocity. And it all starts with defining what scalars versus vectors are. So let's start off with what a scalar is. A scalar quantity is simply a physical quantity with no direction. And often how we refer to this is we simply just say it only has magnitude. So I'm going to write it as only magnitude. And that just means no direction, just simply how much. So that might be another way I phrase it during class. I might just be like, how much distance is traveled, how much in terms of the overall quantity in that case. So a physical quantity with no direction. Okay, now some examples of this are going to be the following. In kinematics, we're going to look at things like distance. So simply how far it takes to go from one place to the other. We may look at speed, which we looked at in lesson 1. We may look at things like time, because how much time? Was it 40, 50, 60 seconds? Was it a couple minutes? Was it hours? What was it? Things like mass, when we get to things in dynamics, we may look at some masses of objects on pulleys or inclines or whatever it might be. That mass doesn't refer to direction, it's just the matter composition. And then we may look at energy, and this would mainly come up in units C and D. And energy is just saying, when I look at the total energy in a system or an energy at any given point, it's not directional, it's just a quantity, it's just how much. All right, now we go into vector quantities, which the sharp distance between a scalar to a vector is simply, it's a physical quantity. So similarly to vector quantities, or similar to scalar quantities, it is still a physical quantity, however, it has direction. So that is a really important distinction there. So when we write this in, it has magnitude and direction. Now, the really big thing I would highlight here, I would just make sure you highlight the width here because we want to be really clear there. And then even if you wanted to highlight under here, you could be like magnitude and direction. And whenever we say magnitude, that simply refers, you can almost think about it synonymously to how much. Magnitude, how much, magnitude, how much. It's just defining the overall quantity. And then the direction comes up when we start talking about vector versus a scalar. Now, what are some examples of this? In kinematics here and further, we're going to focus on the following. We may talk about displacement. And displacement is different than distance in terms of symbol because what we do is we put our vector arrow on top of it. We may look at things like velocity. Velocity being a directional speed, and we'll get to that very shortly. Then we could look at acceleration. Acceleration being a measure of, is the thing gaining speed? Is it losing speed? Is it slowing down? Is it speeding up? And then lastly, force. When we get to unit B and onward, we're going to define forces as having some sort of directional magnitude. And as soon as you know it has directional magnitude, it must be a vector quantity. Now, I want you to notice something special about these. When we looked at lesson 1, we talked about distance, speed, time, and those things all included these symbols of D and V and T, but they didn't include this special little symbol above here. Now, what we want to define is that vector quantity that includes that symbol above, we are going to call our, maybe even like our vector quantity symbol or our directional symbol. So we look at this and we say everything that has this symbol, almost like a backwards arrow in a way, or it kind of looks like a half arrow, we consider this to be our vector symbol for these vector quantities. So just be looking out for that because that is a sharp distinction that anytime we're dealing with vector quantities, we want to make sure we have this symbol above whatever given variable. All right, and now we move into vectors and breaking down specifically how can vectors be represented visually on any given page. And so when we start dealing with vector diagrams, whether that be in this unit, whether that be in unit B, we want to be really clear of how they are overall composed, because it has a big difference on when we start drawing our force diagrams and when we start drawing our overall directional magnitudes, we want to draw these accurately. So a vector can be represented by an arrow, and it's composed of two following parts. So I'm going to maybe consider this to be, and I'll write it in the following way. Let's consider this part 1 and this part 2. Now, what I'm pointing to in part 1 is simply the arrow that's on the front here. So for number 1, the tip is going to represent the direction. So simply it just says, hey, which direction is the motion of this object going? Which direction is the force going? So the tip represents direction. Now for number 2, which represents the body is simply saying how much or the overall magnitude of this thing. So it's saying, like in really, really specific terms, the magnitude. And then in brackets, I'm just going to say how much. Because remember, I want to make these things synonymous with each other. So we're going to try to tie these together as much as possible. The body represents the magnitude or how much. So depending on how long this vector arrow could be, it could be something shorter. So it could look like, let me just get my straight tool there. It could look shorter. It could look even longer than this other black arrow. It could really look any way, but we determine it based on the magnitude or how much. So for that smaller red arrow, or the one below here, we maybe could say this is like 20 meters per second or 20 newtons. For the one above, we could be like, hey, this is 30. And then maybe we say this one's like 40. That's just a visual way of saying that we have different magnitudes. And then the arrow at the end is going to represent the specific direction, whether that be northeast, southwest, up, down, whatever it might be. All right, now vector directions, just like I just alluded to here, we want to draw this out and say, well, if we have all these directions and these arrow diagrams can represent a specific direction, in physics we need to determine the direction by dealing with vector quantities. And so to determine our directions, we're going to use our following conventions around the directions, including the signs that go with those. So what I'm going to do is I'm just going to draw a T up here, and I'm going to do that in black here. So here's my T. And this is just like a Cartesian plane in math. Now, the Cartesian plane in math, we would call it 0, 90, 180, 270 degrees, and then 360. For us, what we're going to do is we're going to label it as north, east, south, and west. Or we're going to label it as up, down, east, or west. Now, this is a really important way to label the Cartesian in terms of physics, because here's how we label all our signs. And it's very, very similar to the Cartesian plane in math. We always say that up in the direction of y is a positive. When we go right on the x-axis, we consider this a positive. When we go left on the x-axis, it's negative. And when we go down on the y-axis, it's negative. So filling all of that in here, if we go right, it's going to be positive. If we go east, it's positive. If we go north, it's positive. If we go up, it's positive. Now, if we go in the direction of left, we're going to make it negative. Left is also west, so we're going to make that negative. South is downwards, so that's negative. And then south and down, meaning the same thing, we also make this one negative. So what I would recommend is, especially when you're first practicing this or learning the physics material, maybe just draw out this Cartesian plane for yourself. And what I'll do is I'll even include this on the front board. So you'll often see that I just leave kind of an extra copy or like a written down out of Expo marker of this, just because it's really important to reference when you're first learning of how do we treat the positives and negatives in terms of vector directions. But remember, it works on the same idea as the Cartesian plane, where we have positives in the north or upwards direction and the east direction. And then in terms of left and down, or west and in terms of this one, I guess I could say west or south, we consider this to be our negatives. All right, now considering the difference between distance versus displacement. Well, distance is a scalar term because it only describes the magnitude of the total position with no change in direction. So the symbol for this one is purely just delta D, how far we travel overall in distance. And so just to really break down this difference here, and I highly recommend in your own notes you highlight this here, because it only describes the magnitude, the total position, that's really important. And then just even that symbol there where we don't have that vector symbol above the D, it's just a change in overall distance. This is scalar, just purely how much. So on the diagram below, let's just provide some labeling here. Originally, they start at the bus stop. So I'm gonna just kind of like circle with my pen here where they start. They start at 0. They then travel out this way. They wheel out 3 meters in the following direction to the right, and then they wheel from that 3 meters right all the way over to 2 meters in the left direction of the original starting sign. All I care about when I'm doing distance is just adding up those totals that represent the overall change in distance. So this would be 3 meters to the right, and I'm just going to literally label it as 3 meters because with overall no directional quantities or specifically distance, which is a scalar quantity, we're just going to add up these directions. And then the person travels from 3 meters right, 5 meters back left. Now, what we're going to do is we're just going to formalize this down below. The change in distance or the total distance traveled is going to be equal to 3 meters plus the 5 meters that the person goes back left. This equals a total of 8 meters in their journey, and we're good to go. All right, now displacement. We need to highlight this huge difference between distance to displacement. Displacement is the net change in position. So we take it from the starting point to the final point only. And so unlike distance where I just took all these things and I just add them up, what I'm going to do is I'm going to say I need to now account for direction, and that direction will have an impact on the overall from where I start to where I end. Now, displacement is a vector term because it includes both magnitude and direction. So from our definition of a vector, it must include the how much plus the given direction. And then the big change we're going to use in the symbol here is just like we said before, if we have vectors, we want to put this little arrow on the top indicating that this is a vector quantity or something that includes direction. Now, let's take a look at the same example that we looked at before, but now account for the overall displacement, aka where they start to where they end. And if you need to write that note for yourself, I definitely would. So person's displacement has a little bit of a different symbol. We write the vector symbol above, and this says from the start to where the person ends. So I'm going to write it like that. Now, let's be specific with that. Above, they travel positive 3 meters or 3 meters east. And so you could write it either way. Either way means the exact same thing. Then on the way back from that starting position, they travel negative 5 meters or 5 meters to the west. Because remember, we're going to look at this and say, well, if they're going left on the Cartesian plane, it's going to be negative. If they're going right on the Cartesian plane, it means it's going to be positive. Now, where did they start? It's really important to indicate that. They start right here and they end right here. Now, what is the difference from where they start to the end? And I will even put that really specifically here. Here's our start. Here's our end. What is the overall distance or difference in that? Well, we would say it is this little component here, and I'll highlight that difference right there. Okay, now, I mean, just purely looking at it graphically, you would be like, or on this number line, you'd be like, okay, well, if they start at 0, which is right in the middle, and then they end at -2, that means the overall displacement should be -2 meters or 2 meters in the west direction. Now, what we're going to do is we're just going to confirm that algebraically below. So below, I'm going to go the change in the displacement, aka where they start to where they end, is equal to, and now I'm going to sum these things together, positive 3 meters in the east direction, plus, in brackets, I'm going to put negative 5 meters, and this would be west. Now, I might just put both of these in brackets because especially when we start including the signs representing the directional quantity, aka a vector quantity, we want to make sure that we don't confuse it with the addition that goes between these, which if I look at these ones here, this is an operational sign, this is a directional sign. And so I don't want you getting those two confused. Operational, directional. Now, what is the overall displacement? We add these two things together, +3 plus a -5. This is equal to -2 meters in the west direction. Now, oddly, these are kind of a redundancy. So if you put -2 meters and the west symbol, you're kind of doing the same thing twice. So how we could write this instead is we could say either -2 meters, indicating it's in the west direction, or what we could put is 2 meters west, like this. So two ways of representing the answer below here. Either way you put it, you could do the combination of both of them, just like we did above. So maybe I'll even write that in here, where we say equals to -2 meters in the west direction. However, it's a slight redundancy, and typically it would only be represented as either the -2 meters or 2 meters west. And so if you see that I'm kind of combining them above, then just watch out for that. But even above here, I typically separate them into their own components here. All right, now, when we look at vector diagrams, massive thing in Physics 20, drawing a vector diagram will visually show you what's going on in a given situation. The big thing we need to take away from this, and I would highly recommend highlighting this, a vector diagram is always drawn from tip to tail, meaning when you start with one vector representing maybe the first leg of a journey or first part of a journey, you're going to draw that first vector, let's call it vector A for the example, and then if there's another vector, we're going to stack it where the tail matches the first tip. And so this tip to tail vector addition gives us an overall resultant or overall magnitude of what's happening with its given direction. So be really looking out for this. I would star this. I would just make sure you review this after the lesson just to make sure you're okay with this tip to tail vector addition. And this is going to go with forces. It's going to go in kinematics. It's going to be a very critical piece to our learning in this unit and moving forward. All right, now let's try out a couple examples of this using our idea of vector tip to tail vector addition, just to make sure we're okay with this. So a person walks 10 meters east and then 20 meters west. And then finally 5 meters east. Determine the distance the person traveled. Okay, so what we're going to do is I automatically recommend just drawing out the overall diagram that represents this whole situation, because it's going to make things very visually clear, which will also help us make it mathematically clear. Okay, 10 meters east. So I'm going to draw that, and I'm going to start by drawing this here. And then I'm going to label it. So I'm going to go, this is 10 meters. And now, do I really need to put east? Not really, but maybe let's just do that just to make sure it's really clear. Just because when we actually draw out our vector, our specific vector arrow, the tip is already indicating the direction. So we can put it in or not, either way. Now, 20 meters west from that. So what I'm going to do is I'm going to go 20 meters west from that position. If I go 20 meters, remember, it has to be longer in terms of that vector arrow. And I'm going to make sure this is a straight line here. It has to be longer because the magnitude is represented by the length of this arrow. So that's going to be 20 meters in the west direction. And then lastly, they say they travel 5 meters east. And so I'm going to draw one more vector arrow that looks smaller than the other ones and is proportional to the size of being 5 meters. So this is 5 meters in the east direction. And again, do I really need to write in the east, the west? No, not really, because the vector arrow or the diagram actually represents the direction itself, but we're good. Now, one thing I'm going to write on here is the following. I look at this and I'm going to indicate that this is the start, which I'm going to call S. And then what I'm going to do down below is I'm going to draw this in and put an E indicating that this is the end. And let's make sure that's a little bit neater there. So this is our end. Okay. Excellent. So when we talk about determining the overall distance the person traveled, remember, distance is purely a scalar value. It doesn't matter in terms of direction, it just matters how much overall. So what we're going to do is we're just going to add these all together just to make sure that we're good to go in terms of the total distance. So I'm going to underline this even. The distance is purely the total traveled. Okay. Now, if I add these all together using the proper notation, I'm going to go delta D, or the total distance, is equal to 10 meters plus 20 meters plus 5 meters. Now, if I add these all together, I'm going to get a total of 35 meters. And so this represents the overall total distance traveled. Whoops, I don't want to erase my work there. Total distance traveled along these three legs. All right, in the next piece, we're going to continue that example 1. Determine the person's displacement and confirm this with a vector diagram. Okay, what I'm going to do is I'm going to go back and copy this diagram that we've already put together here. And so if we can copy this diagram, it should help us directly get our solution for the piece we want here. So we're going to copy it. I'm going to bring it over to the next page here. We'll paste it in. Awesome, there we go. And now we're just going to add something else to this diagram, because in the last piece we were looking for overall distance, just meaning we added up all the values. For this one, we want to look at where we started to where we ended, and that's going to determine the overall displacement. And then we can confirm that mathematically or algebraically. So just looking at this visually, if this is my ending position, and I'm just going to draw a straight line up like this, and this is my start position, I'm going to draw a straight line down. We're going to consider this to be our 0 meter position, right where we start. Well, if we end to the left of that, meaning our ending spot is this way, how far did we end up on the left-hand side? We ended up, in this case, you go 10 meters right, you go 20 meters left, which means over here would be -10. So I'm going to write that in. That's -10 meters here, meaning this is going to be -5 meters from the start. And so just using prediction, we should get that a delta D, or delta D with the vector symbol, aka the displacement, is equal to, by prediction, -5 meters or 5 meters in the west direction. Remember, you can write it either way. Now let's show this mathematically. So delta D with the vector symbol is equal to, let's be really, really good with our signs and notation. In brackets, I'm going to put +10 meters in the east direction. And then I'm going to close that, and make sure you're putting square brackets on your directions, close bracket, plus -20 meters in the west direction. And then I'm just going to move this down here just so that we can fit it all into one line. If I move this piece here, this is going to be positive, and then we went 5 meters back in the east direction. There we go. Now, if we sum these all together, we're going to get an overall displacement of +10 minus 20 is -10, plus 5 gives me -5 meters, or 5 meters in the west direction. So just like our prediction, based on our visual that we created, we get the exact same answer here. Now, one thing I'm going to really stress here, please make sure you have this. Everything needs to be included in terms of, if it's displacement, that vector symbol better be above it. If it's a vector quantity, it also must have the sign representing direction. Remember, these represent operations. You don't want to get it confused with a positive outside these brackets is just saying the overall operation is being adding these things together. What's happening in the brackets here is some sort of sign that represents direction. So you want to be really clear with that. And then lastly, your answer could appear either way. What I would get in the habit of when you're practicing is just show it either way, so that when it comes to a multiple choice or some sort of short answer, if they ask you to put it in one way or the other, well, you know that you could do either way. All right, now get in the habit of adding the vectors and adding a negative sign after if necessary. Now, what does that mean? It means let's just make sure that every vector we do is added. So the sign I put between the brackets, I never put a subtraction symbol. I never went, oh, well, I know this is negative, so I'm just going to make this negative out front. No, what we're going to do is we're just going to get in the habit of put a positive between them, and then in the brackets, put the directional sign. So whether that be positive or negative in the brackets, and then that way you'll never make a sign mistake. Don't just make a quick assumption and be like, oh, I know this is negative, so I'm going to put negative. Just put an addition there. Really, really good note that we should hold on to, that you should bring with you forward. All right, now here's our two formulas side by side. What you're going to notice is that on your formula sheet, well, not only is the difference here of VAV and then VAV with our vector symbol above, that's one difference you may notice, but the one thing I want you to notice right away is that when we're talking about speed, it doesn't include the vector symbol. When we're talking about velocity, it includes the vector symbol, and that's a really important piece here. And then specifically, if we're talking about velocity, it's the change in an object's displacement over a change in time. So no longer, just like we did in lesson 1, we just took our total distance and divided it by the total time to get average speed. No longer are we going to do that in terms of when we talk about velocity. We need to figure out, first of all, what is the displacement over the total time. And you'll see what we mean just in a second here when we move on to our example. Okay, suppose we have the following example. Example 2. Mr. R drives 300 kilometers north from Calgary to Edmonton, and then immediately turns back and drives 450 kilometers south to Lethbridge. The total time for the trip was 8 hours. For this problem, assume that Mr. R drives at a constant speed the entire way. Okay, so what we're going to do is we're going to draw out a vector diagram for the situation. Really, really important. So we're going to draw out a visual, and here's how I'm going to do it. I'm going to label the 3 following cities. So I have right in the middle here, we're going to say we have Calgary. There we go. And then north of that, we're going to put Edmonton. And then south of Calgary, we're going to put Lethbridge. Now, I know these aren't proportional or exactly where they're located, but we know generally Edmonton is north of Calgary, Calgary is north of Lethbridge, so in this order, we're good. Now, we're going to label it here. So I want to put the following. We go up 300 kilometers from Calgary to Edmonton. So I'm going to put a straight arrow that links these two here. Okay, now I'm going to put a label with it. So this is our 300 kilometers. And I'm going to just put the symbol north. There we go. And then from there, Mr. R immediately turns back and drives 450 south to Lethbridge. And so I'm going to draw another arrow, but this time it's going to be going down this way. Now, one thing you notice is that the arrow is longer for the blue one or for that second leg of the trip because it's technically has more magnitude. And so in a vector quantity, it should be represented by a longer arrow. Now, let's just make sure the label is on there. So this is going to be 450 kilometers and in the south direction. Okay, now draw a vector diagram for this situation. There it is. The only thing I may add to this is that this right here, Calgary, is going to be our start. In Lethbridge, this is going to be our ending position. And so that might be the one thing you want to write in there. That would be an important detail. All right, determine Mr. R's distance traveled and the displacement. Okay, so we're going to resort to this diagram. So I may be flipping backwards and forwards between the two. If we look at this diagram, well, the overall distance is simply just take those two amounts and add them together because it doesn't matter direction. We just simply say for scalar quantities, how much. And so in this next piece here, we're just going to add them together. Okay, now for this one here, for distance, change in distance, we're going to go 300 kilometers plus 450 kilometers. This gives us a total distance for this trip of 750 kilometers for this overall trip. So I'll make sure to highlight that just so we have it all copied and saved. Perfect. Now when we go on to displacement, here's how it's going to differ. Delta D with the vector symbol above is equal to, now we have to be really careful with signs here. In brackets, was the 300 kilometers positive or negative? Well, when we looked at it, the 300 kilometers was going in the north direction or the up direction. So we're going to consider that positive. Positive 300 kilometers. And just to be really specific with this one, I know we said it's a bit of a redundancy to put positive and north, but I want to be very clear with the problem. Plus, remember, this is just operational. It's not a directional sign. In brackets, we're going to put our 450. If I go back to the 450, remember, that was the drive from Edmonton all the way down to Lethbridge or in the south or down direction. And so it's going to be negative. I'm going to put negative 450 kilometers. And again, we're going to use a little bit of a redundancy, but I'm going to put south in the square brackets. Now, when I put these two things together, this is like saying positive 300 minus 450. That's equal to negative 150 kilometers. Or what we can do is separate this and say it's 150 kilometers in the south direction. So the overall displacement from Calgary to the original or to the new position is going to be equal to that 150 south or negative 150. So remember, you could put either one. I know it's a little bit of a redundancy to put the positive symbol and the north and then the negative and the south and then answer it in individually like this. But realistically, I only put the positive and the north in here just to make things clear when we're first learning it. But just know your answer could appear in either of these formats as long as you understand that south or down is negative, that's perfect. You can use the negative version. And then in terms of the 150 south, if you want to do that, this actually might be better when we move on to our next piece where we start breaking our vector diagrams apart and we're taking things that have angles and breaking them into multiple vectors. So later down the road, it may be helpful to just write them like this and be familiar with this notation, but either way is fine. Now, lastly, determine his overall average speed and velocity. Okay, so let's do the speed calculation first. The speed calculation can be the following. VAV is equal to the total distance of the trip divided by the total time. Now, that means that the VAV is going to be equal to, remember when we added up the total distance, it was 750 kilometers from above. And we're going to divide it by the 8 hours that constituted the entire trip. Now, when we type that into our calculator, we are going to get 93.8. So VAV is equal to 93.8 kilometers per hour. And let's highlight that answer. Now we're going to move on to the overall velocity calculation. VAV, or velocity av, because we're going to put the vector symbol above, is equal to the change in displacement, or from the start to the end position, divided by the total time. Now, from above, we calculated that if the velocity average is equal to this, it's equal to 150, or we could even just put in a negative symbol here. You could put in 150 kilometers south or the negative 150 kilometers divided by the 8 hours the trip took. We get the following. Velocity average is equal to, this is negative 18.8 kilometers per hour. There we go. So we're going to highlight this piece here. Now, again, we could answer this in the other way. If instead we wanted to do where instead of the negative, we went 150 kilometers in the south direction, all we would change in our final answer, because this would still be 8 hours, we would say velocity average is equal to the 18.8 kilometers per hour, but instead it would be in the south direction. So either of these answers would get you full credit on any sort of assessment or full marks just generally. So you want to be very, very specific about these. Whatever way you go, either way will be good. Just remember that it could appear either way on an assessment. All right, now we have finished the lesson for lesson 2. Make sure you get as much practice as you can on these. In fact, I would try to just complete all the practice problems because it's really important to take care of all the notation and really understand the difference specifically at this point in Physics 20 of the difference between a scalar and a vector and how it relates to distance versus displacement, speed versus velocity. If you can really nail that down right now, that's going to really set you up to be successful in the rest of the semester, especially because the definition of a scalar versus a vector quantity comes up repeatedly and appears in all 4 of the major units.